Okay, good morning everybody. This is Mrs. Foram M. Joshi from GH Patel Engineering College, Vallabh Vidyanagar. We'll continue with the fourth chapter where we have studied about the band theory of solids and PN junction diode and somehow about Zener diode. Now we have studied the construction of the Zener diode, but we have not studied, we have just left the portion of voltage regulation and types of breakdown. We'll take the types of breakdown first. What are the types of Zener breakdown? Why Zener breakdown occurs, that we have studied that in the reverse bias, whenever the diode is connected with the reverse power supply, the electrons, the minority charge carriers, will be breaking the bonds and they will move to the conduction band for the conduction, and at a particular value of the reverse breakdown voltage, the number of broken bonds increases enormously and there is a large current in the external circuit. So that is called the breakdown. Now this is actually the Zener breakdown. What about avalanche breakdown? Avalanche breakdown is the second type of the breakdown mechanism in which the breakdown occurs in a very regular form. When this type of breakdown occurs, what happens? The electrons will move and breaks the bond, and when these bonds are broken, there will be some kinetic energy due to the external reverse bias voltage will be there, and this excess kinetic energy, electrons will be moving in the conduction band. These electrons, when they collide with another steady atoms inside the PN junction, they will be colliding with them and they will release some more kinetic energy, some more electrons, and due to this there will be a multiplication process. That means one electron will break one bond, and there will be, as a result, there will be two electrons which are in conduction band. Again, these two electrons will break two more bonds, and there will be four more conduction electrons. So you will get a chain reaction in this process, and you will get the current in the external circuit in a regular form. Of course there is a breakdown, but there is not a sudden breakdown. You will not get a suddenly height in the value of the current, but you will get a regularly increasing current. So this is called the avalanche breakdown. Avalanche means the fall of the ice from the hills, right? So with the similarity in the process, in the shape of the IV characteristics, this type of breakdown mechanism is called avalanche breakdown. I'll show you how this avalanche breakdown characteristics can be drawn. One can see that in the reverse bias characteristics of the Zener breakdown, one can have VR as the reverse bias voltage and IR, which is in microampere, as the reverse bias current. And now this is actually the reverse saturation current, and this type of breakdown occurs when Zener mechanism plays a role, right? And here is your VBR, the breakdown voltage. But now when the avalanche breakdown occurs, avalanche mechanism says that it is a regular breakdown. So after the reverse saturation current, there will be a very regular breakdown occurs, and one can have this Zener breakdown is in this form. One can see that here is the breakdown voltage VBR, and we can see here that with this reverse bias voltage, this breakdown has a very regular shape. This is actually a perfectly knee shape, sharp shape. Here is a knee shape, of course, but it is not a sharp breakdown, it is having a regular change. This is called avalanche breakdown. And in this avalanche mechanism, the reverse breakdown voltage, it may vary from 5 to 8 volt, and for Zener diode, for normal Zener diode, it may vary from 3 to 5 volt, right? So this is the difference between Zener mechanism and avalanche mechanism. depending upon the applications, which type of Zener diode is used, that is decided in the circuit. Now what about the voltage regulation of the Zener diode? One can see here in the slides that in the Zener diode, in the Zener voltage regulation, we have joined the Zener diode on the breadboard. We have supplied 0.5 volt 33 ohm resistor, and we have given a power supply, and that is actually from AC input, and we have a 7.5 volt Zener diode. So the tag which is said that it is to the camera, it gives you the output in terms of the voltage, which is a regulated voltage. Now we can see the real circuit, the schematic circuit of this type of Zener diode. The schematic circuit says that if this is the unregulated power supply, and from this terminal, if it is given to the Zener diode, of course it should be in the reverse bias to the Zener diode, this limiting resistor will limit the power supply, and then here as a load resistor there will be one resistance. This resistance can be put here also, because this is your source voltage, and here is the limiting resistor. This is actually load resistor, and in between the load resistor one can have the V output, which is the regulated power supply, right? So what happens when this circuit is switched on? When the unregulated power supply is switched on, this limiting resistor will resist the power in terms of the voltage it will give to the Zener diode. Here we have used a 7.5 volt Zener diode, so at 7.5 volt of the reverse bias voltage we can get a large amount of current in the circuit, and due to that there will be voltage drop across RL, and in RL if we measure the voltage across RL, then we can have a constant regulated power supply. The excess voltage drop is taken by the Zener diode itself. One can have the Zener characteristics in the slide. It is one and the same as we have seen in the on the paper. Zener voltage is here. It is actually the breakdown voltage, and the region of voltage regulation can be seen after the breakdown voltage, and this current is limited by the maximum power dissipation. The maximum power which can be taken by the Zener is the IZ max into VZ, and of course the forward characteristics is one and the same as the simple normal PN junction diode. So there are so many applications for voltage regulation, and this application consists of the laboratory voltage regulation in our simple regulated power supply. This type of circuitry is used with some complicated external circuitries, and apart from that, in simple devices, electronic devices that we use at home, this type of voltage regulation circuitry is used, so that our devices may be saved from some sudden increase or decrease in the voltage, right? Now we'll move ahead to next component, that is the varactor diode. Actually it is a semiconductor diode which operates under the reverse bias condition, which is a voltage dependent variable capacitor PN junction diode. Now what is this voltage dependent variable capacitor PN junction diode? Actually this says this is actually the symbol. The first figure here is the symbol anode, cathode, diode, and you can see that at the end, apart from your simple PN junction diode symbol, N type symbol, you have a capacitor symbol, and on the right hand side figure there are different varicap diodes are shown. Yes, this is also called a varicap diode because it has the variable capacitance. How it varies the capacitance? Let's see. The depletion region of a junction diode has a large concentration of positive charges stored in the n side of the junction, and a large concentration of the negative charges on the p side of the junction. It is separated by a distance w. And what is this distance w? It is actually the depletion region width. This is the simple p-n junction diode basics, right? We know that this occurs. Now what is the consequences of this type of large concentrations of positive and negative charges? The consequences is this situation is similar to a charged capacitor where parallel plates are oppositely charged, means one plate is positively charged and another plate is negatively charged. So in between these parallel plates there is a dielectric region, right? And due to this there is a capacitive properties for those two parallel plates. So here in the p-n junction diode, the depletion region is in a junction, it leads to the junction capacitance. That means the p-type material acts as the positively charged material and the n-type material acts as a negatively charged plate. In between them there is a depletion region which acts as a dielectric material. And that if we measure the capacitance here, then we can have a particular value of the capacitance which is of the order of course picofarad. Say from 1 picofarad to 100 picofarad value may be there, and this is called the junction capacitance or barrier capacitance, right? And of course there are two types of capacitance. One is the diffusion capacitance and another is the transmittance capacitance. We are interested in CT capacitance, that is transmittance capacitance, that is equal to EA or say epsilon A upon W, where capital A is the area of the cross section of the material of the junction, E is the permittivity of the semiconducting material, and W, as I said earlier, it is the width of the depletion region. Now this CT can be measured, can be dependent on what? It is dependent on the width of the depletion region. Now width of the depletion region is the only variable which depends upon the reverse bias voltage. For the forward bias this width is very thin, and for the reverse bias it depends upon it becomes larger. So ultimately CT depends upon two factors. First is reverse bias, another is the doping concentration. This reverse bias voltage is or you can say that CT is proportional to 1 over under root of VR, and as the doping concentration changes, the reverse bias width will be also changing, or say the depletion layer width will change, and again due to that there will be a change in the junction capacitance. Here is a typical junction capacitance graph. It is actually the capacitance versus the control voltage graph, and one can have the varicap diode terminal capacitance on the y-axis and the voltage on the x-axis. When we can see here that it is actually exponentially varying capacitance graph, and the capacitance is measured in terms of picofarad. From very high value it is going to the very lower value, but it is not becoming zero, it is going parallel to the x-axis. So before we go to the applications, we can have I have this type of characteristics graph of the varactor diode, which shows the doping concentration versus the doping concentration value or doping type versus the capacitance of the varactor diode. Now in the first graph we can change actually the factors, the doping factors, from hyperabrupt to linear. The relationship between voltage and capacitance of a varactor diode, that depends upon the doping profile, and there are three different types of the doping profile. One can see here that on the first graph it is the doping versus the depth of the, or say the width of the varactor of the diode, and this slide bar can change to the doping concentration from hyperabrupt to abrupt to linear. Initially we will put it on the abrupt side, and we can see that here is in the second graph we can have the capacitance versus voltage graph, and capacitance is measured in picofarad, actually it is actually on a logarithmic scale, one can see here that the resulting voltage capacitance curve shows that from say 9 picofarad it is decreasing with increasing voltage. If I change the doping profile to the linear, whenever the linear doping profile is there, the initial capacitance is higher, and this capacitance decreases as it goes to higher voltage. The inverse situation occurs in the hyper-abrupt doping profile. In the hyper-abrupt doping profile, we can have a very high value of doping, right? And due to this, very high value of impurity concentration, and due to this we can have a very larger amount of capacitance. Now what is the use of this capacitance? We can have that if we increase the doping into the PN junction diode, we can say that the capacitance increases enormously. So one can say that at a constant doping profile, if we change the reverse bias voltage, we can have the change in the capacitance with only providing the voltage. We don't have to put n number of capacitors in our circuits. Now what are the applications that we will see in this slide? It is the applications are in TV receivers, FM receivers, tune devices, communication devices, and band pass filters. Now what is this this type of devices do when we want to tune something on the tune some frequency in an LC circuit? You must have learnt about LC circuit, right? What is a simple LC circuit says to you? That it has one inductor and one capacitor, right? You may have learned this, but just for the revision, for the sake of revision, we can say that this is VCC and another end is ground. When VCC is provided to this circuit, this is actually LC resonant circuit. Why it is called resonant circuit? When VCC is provided to this circuit, the capacitor and inductor will charge. Capacitor will be charged and discharged continuously, and when it is discharging, the inductor will have the energy, amount of energy into that, and after the capacitor is fully discharged, the inductor will give the energy to the capacitor, so that there is a resonant frequency which is formed, and this frequency can be given by 1 over 2 pi under root of LC. You must be familiar with this equation, right? And this 2 pi under root